Hi, everyone. So today I'm going to take you through a little bit of a journey of what's going on in the machine learning community and why you should even care about it, and what are the practical challenges that we're facing with machine learning in this industry and how we're going to tackle some of those things long term. So I think one of the things is, and everyone in this room is aware of this, is that, you know, real applications and deployment of these robots wasn't until 1961. The big thing is, though, is that computer science has, at this point, a 20 to 30 year head start on robotics. So if you look at it, this robot was deployed. It had a magnetic tape drum that all of the code was run off of. It wasn't actually driven by a computer, and it was a static process. And so I think that when you look at it later, in 1969, when Shanky hit the field, and it's kind of the future of robotics, and some of the stuff that they did at the time was pretty impressive, although it took about 8 hours to navigate a room that was about 10 foot by 10 foot. So this room, this whole video that's here is about an 8-hour time-lapse video to go around that block. But at the time, what was really interesting is they actually used RF signal to go to a large bank of computers that were all programmed by punch cards. Yes, punch cards. And it would basically take a single black and white image, compress that image, transmit digitally, or analogically actually, back to the computer bank, and then process that image and then decide what to do. And it took forever to do it. Today, we do this in 1/20th of a second or faster, maybe 1/200th of a second for these kinds of navigation behaviors. But this was the beginning of ML. But one of the things is that from this, a lot of people started saying, this is the dream, magic. You know, we had these things, now we have this. It automatically assembles all of this. But the problem is when you look at this, and this is a really cool and slick demo, there's no machine vision involved in any of this. There's none. The robot is already pre-programmed, it's heavily fixtured, and unfortunately, the problem is to make it do this thing, it took all of this programming. And this is not scalable. This doesn't lead us to where we really want to be, which is robots knowing what we want them to do and then doing them. And this takes a highly skilled engineer, and as Jeff said this morning, there's not that many people to do these things, and there's a large skill mismatch. And so we have to start looking at how we solve these problems. And a lot of this is motivated through machine learning. And a lot of people in the last 5 to 10 years have really looked at programming by demonstration, for example, in the case of like a Rethink robot, as the kind of the groundbreaking thing that changed so that we could make these robots easier to program and things like that. Unfortunately, the thing is that programming by demonstration, although by a teach pendant, has been around for about 30 years. In fact, what's really interesting in this video is from around the end of the 1960s, the early 1970s. In the voiceover, one of the big things that they say is the groundbreaking capability with this teach pendant is it can do a linear transit. Like, yes. And that was really groundbreaking at the time because it was around the same time that we had actually got transformational math so that we could do a straight line transit. Before that, we really couldn't. We basically had to put in iterative points to make it do that transit, and that isn't as easy as this was actually doing a computation using transformational math to do this straight line transit. And of course, you know, when you talk about teaching by demonstration, it's also called kinetic teaching. There's lots of demonstration that shows that kinetic teaching is better than teach-pendant programming. But this doesn't really get you to machine learning, although we're getting close to that, because with planning by demonstration and teaching by demonstration, what we do is we do a perturbation of the paths that we've learned so that we can do what are called experience graphs. So it takes the experience that it has, and it perturbs that to do new things. However, we're not doing that, but we are doing it so that we can scale these things to larger robots in the case of this Energid video for master-slave techniques for planning, teaching by demonstration, et cetera. And of course, even now we're getting more into the app space so that we're trying to make it easier for people to program these devices using apps and all sorts of other different types of set points so that people who don't have the technology education can use this technology. However, you're probably wondering, well, where's the machine learning? So the thing is now you're starting to see some companies start to use machine learning to do some of these activities in terms of doing the recognition of the text on the screen, doing some of the perturbation I was talking about. In this case, you had to demonstrate it on one of these machines, and then it could basically use that for all of the machines in the array. But I think that one of the things is once you start doing something like machine learning, and this is from John McCarthy, the guy who said, kind of created the terminology AI, said once it's working, no one calls it AI anymore. And this is one of the things about the difference between AI and machine learning. So AI is aspirational. There's no such thing as AI. If someone says they have AI in their thing, they're most likely blowing smoke. And it's because AI is aspirational. It's the idea of learning to learn. So when we go to college, we learn to learn. When we go to high school, we learn to learn. Our whole lives are centered around learning to learn. But when we teach machines, we teach them how to do a task. So we teach them, they learn to do a task. A machine is learning to do a task, but it's not learning how to learn to do a task. And that's a very big distinction. But the thing is that this is the other big misnomer with it is once it's working, so in the 1980s, and I don't know if anyone knew this, optical character recognition was considered the forefront of AI. So that thing that you use to deposit your checks today, that was the forefront of AI in the 1980s. And yet, this is one of the more advanced pieces of optical character recognition running against all the text here. And you can see that it's totally messing up. And if you look at it, the way we use machine learning today to improve these systems is through, for example, reCAPTCHA. So you guys know when you go to a website and it says, "Are you a robot?" ironically. And it shows you that blurry piece of text that looks like it came out of a book or off a street sign. So that's called reCAPTCHA. So it's actually using all of you as a whole bunch of trainers. So when you type in the text to that, it's actually improving an algorithm in making the machine learning, the algorithm behind text and speech recognition, better. And so you're actually, every time you type in that thing, you're helping a piece of machine learning improve. However, it still has a long way to go. And I think that another thing is when you look at the types of ways that we're doing machine learning today, this is some groundbreaking work that Google kind of put out showing that they could basically, and this poor guy had to open and close this door thousands of times for all of these robots to demonstrate how they could teach robots to generically learn different handle structures and grasping strategies for opening and closing doors. But as you can already imagine, this is not scalable. So they had a whole bunch of mock-ups of a whole bunch of handles with a whole bunch of doorknobs, and a guy for weeks on end opened and closed these doors for these robots. Now, if you want to do this for the entire scape of all of the things that we have in the universe, this is a lot of work, and this doesn't scale. And so when we look at machine learning, we're starting to look at other types of reinforcement learning. So this is kind of an experience learning. This is how you go from planning by teaching by demonstration to actually learning a whole task. And so here we're learning how to flip a pancake, and he is very easy to do it. People are very good at these kinds of things. Unfortunately, on the first time of reinforcement learning, we can't even get it out of the frying pan. And it's not even until the third try that we even get it to fall onto the floor. And so this is the state of the art. I hate to break it to you. This is the state of the art in reinforcement learning. I think it takes something like several hundred trials for this thing to actually be 100% successful at learning this one kinesthetic task. So now if you look at what it means to really talk about teaching by demonstration to robots, you can already start seeing that this probably isn't the way to go for doing machine learning, for teaching robots to be capable. And the other thing that's really important about this is all of the vision is off the robot. And so in order for a scenario like this to work is you have to have all of this vision system to make this robot capable of doing these tasks. And it eventually gets it. So the other thing that people are starting to do is they're starting to look at how recorded scenes or recorded imagery can be used to train robots to generalize behavior. So this is some pretty groundbreaking work at Google. Basically, they trained a robot in simulation, and then it had to learn how the kinematic movement translated to the body of this robot. And one of the things that was really interesting is they never taught the robot that it had a torso link so it could get taller or shorter. And so that was actually inferred through the algorithm, that extra kinematic link. And so they used the process of supervised learning. So after they taught the robot and the robot made some assumptions about how this was supposed to happen, they would say yes or no, this is a good or a bad behavior. So it's somewhere between supervision and self-supervision eventually. So at the end, they did no human supervision, but it had a lot of steps in between. And when I was talking about video, I mean, the internet, yes, it's full of cat videos, but it's also full of other videos, like people making food and things like that. And so a lot of people are looking at how can we take the large scope of data that we have in the internet today, besides the cats, and really make it useful to robots so that they could watch hundreds of videos of, say, Julia Child making pancakes, and next thing you know, the robot is making pancakes. And so some of the work that's going on today, and you can see that a lot of this is limited because this robot's learning how to make this drink, but it's got all of these special tools. But we're making progress in how robots can perceive what's happening and then translate that into a motor activity that does some semantic task. But I think one of the cool things is, and this is some really interesting research that came out at CVBPR about a year and a half ago, is it's really important to really understand the kinematic models of people and how that translates into the kinematics of robots. And one thing that's really exciting about this research specifically is that they did all of this in real time off of just generic YouTube videos. So they were able to use all of the techniques that they have for understanding the different parts of the human body. They used all sorts of different machine learning techniques to basically construct the kinetic structure. But the thing is that this is just one video, and lots of people can demonstrate that they can do this on one video. That's easy, and you've seen lots of that. But then they took it and they put it on random things like this, and who knows what this is. But then they did it on full stadiums of people at basketball games, and they were able to do this, and these kinematic models held up in full action scenes, tracking people doing live, real action. And so now imagine as we look towards making more humanoid-shaped robots and things like that, this gives us a real leg up for having models to teach robots how to do things. And then the other way that people are really looking at this is, can we teach robots to do things in simulation so that we can do exponentially iterative models for the robot to try and fail millions of times. So this robot actually never saw any of these blocks in real life before it did this task. It was trained to do this entire task in simulation before it ever got the real world experience. And so this is a really interesting way of looking at how we might be able to scale teaching robots. And what's really cool is they, in simulation, put in all sorts of random noise to make sure that the robot could handle all of these different contingencies and iterations. And so it also looked at how you would deal with, temporal replayback, and if the robot had started at some configuration, not the blank table with a whole bunch of blocks on it, but a stack, it could actually go forward and backwards through that learned experience to figure out what the next step was in the stacking activity. But the problem is that with data, there's some challenges. And I think this is one of the things that we don't really talk about the skeletons in the closet of machine learning. And one of the skeletons in the closet of machine learning is these systems are very hard to introspect, and it's very hard to understand why they do things. We make these systems to do really cool things, but we don't always understand why. And a great example on the right-hand side is this husky versus wolf. So they made an image algorithm that basically was supposed to tell the difference between a husky and a wolf. And they put a data set through it, and it came out and it said, this is a wolf, or this is a husky. Yeah, this is a wolf, but it's obvious that it's a husky. And so the researchers went back and they said, okay, we're going to make a piece of software that's going to explain how it made this decision. So it's going to show the part of the image that it used to determine whether this was a husky or a wolf. And as you can see, they made a really fancy snow detector. And so this is one of the skeletons in the closet of machine learning and AI, is that we talk about large data sets and we talk about how we can take all of this data and magic will happen at the end of it. But the challenge is that do we really understand how it got to that magic? And this is really important when you look at things like safety and determinism. And so we can greatly impact the outcome of a learned behavior based on the data that we're given. But if we don't understand how the data is being interpreted, we have a problem. Another thing that people misunderstand, and so we'll talk about the image on the left, is that people have this impression that image recognition is solved. It's not. Yes, your Facebook can identify your friends. Let me give you a hint. It knows who all your friends are. So it greatly reduces the number of people it has to compare to. You probably have less than 1,000 friends, so it only has to compare the images, the random images that you take, to 1,000 individuals at most, unless you're really cool. And then, but it's not billions of images. And so they already have a narrowed scope to do that comparison. And the thing is there's also a lot of value that you put into taking pictures. You do a lot of processing. You are an awesome image processing robot. So you do this cool thing for machine systems. You actually center the person's face typically. It's usually well lit. They're usually smiling. And all of those things actually help these algorithms understand that that's a person. But when you look at larger image sets, so the image on the left is from a data set called ImageNet. It has 15 million distinct images in it. They're taken in all sorts of lighting conditions, all sorts of different scenarios, people looking at the image, people looking away. And the best recognition algorithm on this one data set, just this data set, and this is a competition that's run every year, is 90%. That's the highest recognition they've been able to get, and it's only on a data set of 15 million. There's billions and billions of images in the world that we're not accounting for, and so I think that what I'm trying to say is that the trouble with data is that we have to have it, then we have to understand how we use it, and then we have to realize that once data sets become very large, it becomes very hard to make machine learning algorithms today that can actually fit these data sets well. And that's demonstrated through some of the best people in machine learning today can still only do 90% recognition on a data set of 15 million images. But the thing is that, when you look at how data is generated and how do we get more of this data and how do we create more data that's interesting for these machine systems to use, so there's this thing called generative adversarial networks. It basically is two computers trying to trick each other. So in this case, and this is because the internet is full of cats, this is really why. And the first generative adversarial networks were trained on cat images. And so basically, one computer is saying, I bet I can make a cat image out of a composite of different cat images and trick this other computer to believe it's a cat. And all of these images that you see here are actually generative images. They're not actual images taken by anyone. They're actually images created only by a machine. But the thing is as we look through the images, everyone in the room probably agrees that's a cat. Everyone in the room, that's kind of a creepy cat, but it's still a cat, right? But unfortunately, the computer thought that that was a cat. And so these are the things that we struggle with these data sets, but we're using these generative adversarial networks to create more data so that we can improve these systems to make machine learning better, so that we can actually get to some of these dreams. And I think that when you look at it, the scope of what they're doing today is it's also enabling them to do very complex things, like find things that are hidden or occluded. So one of the problems with robots is they typically only have sensors from one point of view, and then they try and find the image. And in this case, they actually demonstrated that they could make a generative adversarial network for determining where spam was. And so this robot actually never saw any of the real data. It basically was trained just on image sets. Yeah, they were very, very creative with their spam. But I think that this is a good example of how people are starting to use these things to train these robots to do activities based on things that they've never seen. And that's where we really want to get to, because if you want to do generic things in the world, you don't want to always show it everything it needs to see to do it. And so by having these kind of methodologies, you can get to scenarios where you can put robots into the world and they can, with the data and the learning that they had previously, act and create value. And so I think the other thing is like, this is really interesting because the robot is trained to try and, it doesn't even understand its own kinematics. It's trying to understand how to move this puck around to achieve a goal. And so the robot, oh, maybe it's not starting. Okay, the robot is given some arbitrary goal, and it's then trying to do this without understanding really the kinematics of anything. And I think that this is somewhat of an artificial way, but the kind of concept. But the thing is that they're doing all of this through kind of a what's called a convolutional network. So they're basically using different types of data to get to this end state without actually knowing much about either the puck itself or the robot arm itself. In fact, they only know stuff about the end effector, so they don't know anything about the kinematics between the shoulder and the end effector. And I think one of the things is that when you look at Fetch and how we use this information, how we help the community move forward with this, is so today Fetch sells a research platform. We sell it in addition to our commercial product for helping to advance the state of machine learning and robotics. And if you look at it, we've sold it to a lot of different universities. All the blue and white robots that you saw in those videos are actually videos that we have, robots that we have out in the world that people are using to do machine learning. And the cool thing is they're open sourcing it all, which provides even greater value. If you look at the foundation of Fetch, for example, a lot of our initial foundation of our product is actually built on top of an open source stack, including Linux and ROS. And why do you care about this? What's the value of this? And I think the thing is that with machine learning that we can start to create semantic models of the world. And this is an example of, on our robots, this is kind of lifting the covers back. We actually used just a learned model of what robots looked like through thousands of I guess, log files of what robots look like driving around in different facilities. And the algorithm was able to learn what a robot actually looks like so that we can specifically track that type of thing in the facility. And we generalize that to do things like tracking forklifts, tracking people, because once you understand semantically what something is, then you can do something with that information, like slow down for certain types of people, or if it's a forklift, know that the forklift tines might be in the air and you don't want to drive under them. So those are the types of things that you can do. And then when you look at behaviors like this in a queuing behavior, the dumb thing that you could do is just wait until the thing in front of you moves. The problem is if a box falls on the floor in front of the robot, it's really, if they don't know that that's not the thing you're looking for to move, it'll just sit there forever. But in the case of you know the difference between a box and a robot, you can go around the box to execute a behavior like this, a queuing behavior. I think the other thing is that when you look at this, it also enables us to do a lot of different things with body morphology. So this is a robot that is small, and then it grabs the cart and it becomes very big. And so we have different behaviors that the robots adapt based on their body morphology, so how big they are, and this enables them to interact with these larger robots in smart fashions. And so I think that there's a lot of applications to this kind of machine learning, and I wanted to give you a little bit of an insight into why it's valuable and how long it's going to take to get there. But there are some shady sides of the challenges with machine learning, and a lot of it has to do with safety. Machine learning is all cool and everything, but unless it's deterministic, I don't think anyone's going to let you put a knife in a robot's hand and wander around, and we all know this. And so these are the next challenges for machine learning is how do we make these systems introspectable and deterministic so that we can use them in safety-related behaviors. We also struggle with things like this. Much of the algorithms that we have today talk about a single agent doing a single activity. A lot of it doesn't talk about multi-agents doing multiple activities. And so here's a whole bunch of robots working together to try and assemble a chair. And this is not a trivial problem, but there's not much work being done in this field because it is a very challenging problem. But as you can see, I think this, just to get to this point, took like 25 minutes. So one of the things that we're starting to work on are activities like this. And then another thing that we are not really focused on, but we're starting to focus on, is how do we use tools? How do robots use tools? This is a great example. This robot can't reach all the way across the table, but if you give it a tool, if it has a knowledge and understanding of a tool, where it is in its hand and how it can use it, then it can use it to assist itself to do activities. But the types of machine learning algorithms that we have today for these things are very limited. And the other problem is that the hardware like this is very hard to get a hold of. And yes, as roboticists, we're very good at teasing robots. And then finally, who knows? This thing, I mean, you guys have seen all of these videos. I heard from someone that it takes about 40 takes to get one good image, like cool thing, like the backflip video you guys saw, or the one where it jumps onto a table. It's really easy to do cool videos. It's really hard to make it work time and time again, and you guys all know that. And how do you apply machine learning to things like this? We haven't even really started. So with that, I want to thank you, and I appreciate your time.